thank you for joining the first session of a series of online workshop titled Assessment of Performance and Uncertainty in Qualitative Chemical Analysis. This workshop is organized by EURACHEM, the Cooperation on International Traceability in Analytical Chemistry, or the CITAC in short, the EURACHEM, as well as the Health Sciences Authority Singapore. I am Tang Lin. I come from the Chemical Metrology Division in Health Sciences Authority, and I am today's session host and moderator. So in the last quarter of 2021, EURACHEM and CITAC published a guide, which the title of this workshop is derived from. The guide is intended to assist laboratories in setting and implementing appropriate methodologies for assessing the performance of qualitative analysis methods and evaluating uncertainties in qualitative chemical analysis. It was recognized that there are less guidances covering these issues as compared to the topic of uncertainty for quantitative analysis or measurements. So while accredited chemical or clinical testing labs are not expected to evaluate or report uncertainties that are associated with qualitative analysis, it is still important or crucial for laboratories to be aware of the reliability of their qualitative analysis results, because this would in turn help laboratories make professional interpretations to present limitations of their methods to their customers or their stakeholders. So today's session marks the beginning of our series of online workshop. The topic for today is terminology and content of the EURACHEM CITAC guide. So to bring us all on the same ground for constructive discussions over the next 4 sessions, our speakers for today will first introduce the terminologies used for the management of the quality of qualitative analysis. And then the content of the EURACHEM CITAC guide will also be presented and discussed so that information can be better understood and better implemented by users of the guide. So to help our audience reinforce their learning, selected examples from and beyond the guide will be explained. Today, we are very happy to have the leading author of IUPAC's vocabulary on today's topic, and also both editors of the EURACHEM CITAC guide with us. As qualitative analysis has extensive coverage not only in the analytical chemistry field, but also in forensics and clinical chemistry, the organizers have dedicated the next 3 sessions to discuss specific examples from these areas. So you may leave your questions or comments in the chat box throughout the session. At the end of each speaker's talk, I will select 1 to 2 questions depending on the time available for the speakers to address. So you may be also invited to ask your questions verbally if it is not really clear to us. And the last segment of today's session will be reserved for general questions posted throughout the session. So due to time constraint, the organizers would like to apologize in advance if it is not possible for us to address every single question or comment from the audience. And I must apologize in advance also that I'm not sure if we have a translation feature in today's webinar, but I think we do not have. I see some requests from the audience. So without much further delay, may I first introduce our speaker for the day, first speaker for the day, Dr. Gunnar Nordin. Dr. Nordin is the Senior Advisor at Equalis, which provides external quality assessment schemes in laboratory medicine, diagnostic imaging, and point-of-care testing for laboratories in Sweden, as well as other Nordic countries. Dr. Nordin represents the International Federation of Clinical Chemistry and Laboratory Medicine, the IFCC in short, in the Joint Committee for Guides in Metrology's Working Group on the International Vocabulary on Metrology. He is also the author of the Vocabulary for Nominal Properties and Nominal Examinations, Basic and General Concepts and Associated Terms, published by the International Union of Pure and Applied Chemistry, or the IUPAC in short. So today, Dr. Nordin will speak on the VIM4 approach to nominal properties. Dr. Nordin, please.
I will now try to thank you very much for the kind introduction, and I do hope we can follow the discussions. You can switch slide now. So first, a short introduction of what VIM is, because I assume that not everyone knows. VIM is a product of one of the two GCGM guides. GCGM have two guides. One is GUM, the guide for measurement uncertainty, and the second is the VIM, which is the guide for basic metrology. For these, GCGM has two working groups, Working Group 1 and Working Group 2. And Working Group 2 is the one responsible for VIM. VIM was first published in 1984, and the third edition of VIM was introduced in 2008. And next slide, please. So what is JCGM? JCGM is an organization a cooperation between 8 different stakeholders: the BIPM, IEC, ILAC, IFCC, and ISO, and UPAC. And UPAP, that is the International Organization for Physicists, and OIML, the Organization for Legal Metrology. The next. This is my entrance into the working group, which I'm appointed representative for IFCC in the working group. Next slide, please. The current work in the working group 2 is to revise the third edition and plan for the fourth edition of the VIM. And 1 year ago, we distributed a first committee draft to which we have received quite a lot of comments, which we are working on for the moment. The outcome of that will probably be a second committee draft to be discussed. Next slide, please. The very basic terms for metrology, or could be said to be the definition of what a quantity is. And a quantity is one of 3 property types described in VIM. The 3 property types in VIM 3 are quantity, ordinal quantity, and nominal property. And these property types remain unchanged. The concept remains unchanged in the VIM 4. However, the wording of the definition is slightly different. And the idea behind this is that the wording should be more clear to understand, more operationally defined, and as you can see here, a quantity now is defined as a property whose instances can be compared by ratio or only by order. And an ordinal quantity is a quantity whose instances can be compared by order, but not by ratio. And a nominal property is a property whose instances can be compared only by equivalence. So this means that we don't use the controversial term magnitude, and for the nominal property, we have a definition which is not negative as it was in the VIM3. Next slide, please. This is the examples of nominal property, quantity, and ordinal quantity in more verbal descriptions. So if you can click now, this is what is meant by quantity in the VIM terminology. That is, we have the first example with the substance concentration of cholesterol in the sample. The second example, the arbitrary concentration of substance or cocaine in a sample of urine, which are both quantities. But next click, the ordinal quantity is a subset of quantities. So the arbitrary concentration is regarded as an ordinal quantity. And next, the chemical species of a substance is a nominal property in the VIM terminology. Next slide, please. So now we come to the topic of today, the EURACHEM CITAC guide with the assessment of performance and uncertainty in qualitative chemical analysis. And next, the thing is that the qualitative analysis is not defined in VIM, so we have to discuss what the qualitative analysis is. And next slide. And next, yeah. I'm sorry for this animation. So the guide defined qualitative analysis as a classification according to specified criteria. And the next, the qualitative analytical result is a simple statement or categorization of a test. That is a classification. And next. The guide also states that the qualitative analysis for the determination of nominal qualitative properties in chemical analysis. And next, where is meant the ordinal results can also be reduced to binary outcome and treated using the method in this guide by assigning or ordinal classification result as correct or incorrect. So next, these are examples of nominal properties, and next of ordinal quantities, which together are, so to say, qualitative analysis. And next slide, please. This is the properties as regarded in the VIM, where we have ratio quantities, ordinal quantities, and nominal properties. And the value scales for those different properties can either be multinary, numerical, or binary. And next, the qualitative analysis, in my interpretation, are the binary cases for a combination of nominal properties and ordinal properties using VIM terminology. Next, let's have a closer look at the ordinal scale binary results. They are recognized as either 0 or 1. The values could be 0 or 1, or substituted with terms like absence or presence, or negative or positive. Next, the specific or characteristic of those values are that the instances could be compared by order, which means that they have to have some background ratio quantity or an ordinal scale quantity with multiple values that could be compared by size. And the other specific characteristic with these types of values are that they are complementary or opposite binary. That means that if the result is 0 or absence, then it's not 1 or presence, and the reverse. And we are also talking about false positive results if the result is 1 compared to reference value, which is 0, and the reverse. And next, please. The qualitative analysis in the EURACHEM CITAC guide corresponds mainly to the ordinal scale results in VIM4 with binary outcome. Next slide. But then we have the nominal scale results, which also can be binary. And here we are talking about equivalence for the instances, which covers identification of substances, for example. The specific conditions for these types of results are that they are not by necessity complementary. We need a positive identification either for A, if we are reporting the result A, or a positive identification of the result B, if we are having the result B. Next, please. And next. And to some extent, the qualitative analysis in the EURACHEM CITAC guide corresponds to nominal scales results also. Next slide, please. Next, yeah. Now, some of the important terms regarding quality of nominal and ordinal results are traceability and comparability. Traceability and comparability are very well defined for ratio quantities, but within the VIM, unfortunately, we have no definition for traceability and comparability for ordinal quantities. Next. And next. For the nominal property, we have suggested definitions for examination traceability and for comparability of examination results, but these are just theoretically described and remains to be tested in practice. Next. And for the quality of the measurements and examination results in the VIM4, we have, of course, the usual descriptions of quality of ratio quantities, such as uncertainty, accuracy, trueness, and bias and precision, and some others. For ordinal quantities, we have nothing. Next, please. And for nominal property, we have suggested definition of a reliability index or confidence index. Next, please. And next. We have avoided to suggest the definition of uncertainty for nominal property values, which is not defined. And next. Instead, we have the index of reliability or confidence suggested as a definition. And next, please. You can read the definition here. The examination reliability defined as probability that an examined value is the same as a reference value of a nominal property. I will try to explain this with an example. Next, please. This is an example of how we can think about reliability of a nominal property. And this thought example is from the variant identification of SARS-CoV-2 or COVID-19 diseases. So if we, on the left-hand side or left column, see a reference set of nominal properties that are the possible variants of the SARS-CoV-2 virus available for examination. And we do have an examination procedure by which we identify the variant in a specific sample. And on the right-hand side, we can see that of the possible values, for example, B117, we can calculate the probability that that result is in agreement with a reference value. Next, please. So this is how we think it could be possible to describe the probability of a nominal property value. We can also calculate probability that the result is not B117, but maybe some other variants. For example, the B1521, which I think is equal to the Omicron variant of the virus disease. The figures here and the probability figures, they are just hypothetical examples to describe the thought behind a reliability index of a nominal property value. Next, please. Let's have a look at one of the examples from the EURACHEM guide. And here next, please. We can have a look at the example 3, saying that cocaine is present in a sample. And here we have to assume some detection level, for example, 150 micrograms per liter. And next, please. And the index of quality of this result is here stated as a likelihood ratio for correct identification. And the next slide, please. Here are the outcome of the result. Cocaine is present at a certain detection level and the likelihood ratio for correct identification. And next, please. Actually, this likelihood ratio or index is a composite of several probabilities. First, of course, the pre-test probability, but it's also a combination of the probability of a correct identification of the substance and the probability that the concentration has been estimated correctly above the detection level. And these are a composite of two properties, the nominal property identification and the ordinal quantity, which is a quantification. Next, please. So actually, we do have several possibilities here for false negative or incorrect result, that either the substance has been incorrectly identified and that the quantity has been erroneously estimated as below the detection limit. So this is my view of the index for quality of the qualitative analysis in the EURACHEM CITAC guide. That this is a composite index consisting of several different probability, which is a wise way to handle this tricky questions. Next slide, please, which actually is a summary in which I will congratulate the EURACHEM CITAC for a well done work. And I think the examples and what is discussed in the guide describes and illustrates the challenges to describe quality in these types of assays. As I've tried to explain in the VIM guide, we have managed to propose an index of reliability for nominal property or for the identification case, but we have no solution for how to deal with qualitative index for ordinal property values. So for that reason, the combined nominal property and ordinal quantity for the binary case, which is formulated by the EURACHEM guide, is a possible way to treat exactly this types of measurements. And the usefulness and how it is possible to implement in practice remains to be shown. And I look forward to an interesting further discussion on how to treat quality of ordinal properties and nominal properties, which is an important way forward for the word of metrology. And by that, next slide, I would like to thank my colleagues in the Working Group 2 for JCGM and for the work in the IFCC UPAC Committee for Nomenclature, where we have had several discussions of these items during the year. And by that, next slide, I will thank you for listening, and I do apologize for the technical problems, but I do hope that you have had the possibility to catch some of the presentations or some of the ideas behind the presentations. And I thank you for the very nice way to present my slides from Singapore. Thank you very much.
Thank you, Dr. Nordin, for your explanations on the important terminologies. With that, because I wasn't able to look at the chat, maybe I'll just scroll through to see. Yes, there is a question from Michael. Example 3 in slide 16. Does the EURACHEM guide tell that chemistry cannot identify a substance much higher than the LOD, the limit of detection, unambiguously? So maybe this is something which Ricardo or Steve can also chip in to address. So, let me share the screen.
Yes, can you ask Dr. Nordin to reply, or?
I'm not sure I catch the question.
I can probably make a stab at that.
Sure, Steve.
The question is, can we have unambiguous identification? Well, to an extent, of course, we can. There's a sad fact no matter what we do, there'll always be some uncertainty in the world. We've never seen a perfect measurement result. We'll never see a perfect qualitative result, but we can be quite sure. So it's not unusual to arrange things so that there is very little doubt indeed. And that example of presence or absence actually is pretty compelling. So I don't think we would have any reasonable doubt that that cocaine's present in the sample. But even when we have very strong evidence indeed, for example, if you're doing forensic DNA fingerprinting, the likelihood ratios are likely to be of the order of 10 to the 9. So the probability of a chance mismatch is far smaller than the probability of picking a person at random from Earth's population, the human population. But even there, as we'll see later, the forensic community don't report that as absolutely guaranteed perfect match. They say there's a probability associated with that. And one of the unfortunate facts of life is that even though the signals we're looking at tell us that there's a very small chance that the two signals will match by chance, of course, very few laboratories are completely immune to mistakes like mixing the samples up. So there's always a little bit of room for caution. And I think that's where we are. We'll talk later about a little bit about reporting and recommendations from the EURACHEM guide, but I hope that covers the case for now. And I see there's another question. How do you check whether a likelihood ratio is fit for purpose? I think perhaps that can follow a later talk, because we'll be talking about likelihood ratios in about an hour's time. So later this morning, my time, later this afternoon in Singapore.
Okay, thank you. Thanks, Steve. And another question or another comment, there is a fundamental difference appointing a source attribution like in DNA and a typification like substance identification for drugs. Do you have a comment for that?
I'd be interested to know what fundamental difference there is. They're a different kind of thing, but as I think Ricardo will explain, in the EURACHEM guide, we needed to come up with a general definition that works for an awful lot of classifications, and both of them are classifications. A DNA fingerprint classifies a profile as matching an individual or not. Chemical spectroscopic identification classifies a substance as matching a spectrum or not. And as long as you've got clear criteria, then you can treat both of those cases as classifications, matching problems. And that gives us quite a general framework. Of course, there are other considerations about DNA. In the laboratory, we're only concerned with whether the profiles, whether the alleles match. But there are plenty of other considerations to do with whether the crime scene stain came from the defendant and whether it was there for some other reason, whether there's a reasonable reason for it being there, whether there's a possibility of chance and so on. So there are other considerations there, but for the purpose of what we're talking about today, we can treat both of them as classification problems. And that's an advantage, but also ultimately a limitation. If you want to make different distinctions, then fine. But for today, we're treating them all as classification problem. Is it a substance or not? Is it above a level or not? And so on.
Okay, thank you. So I think with that, we need to move on to the next speaker. Thank you, Dr. Nordin, once again for your talk. Okay, let me introduce the next speaker. So I believe you can see the screen now. So I have the honor to introduce our second speaker, Dr. Ricardo Betancourt de Silva. If you have read the EURACHEM CITAC guide, you might find his name familiar. Yes, he is the co-editor of the EURACHEM CITAC guide. And Dr. Ricardo currently chairs the EURACHEM's Qualitative Analysis Working Group, and he is also the Secretary of CITAC. Ricardo is currently a researcher at the University of Lisbon in Portugal. Today, he will deliver two topics for us. He will first cover the objective, the structure and background of the EURACHEM CITAC guide. Ricardo, please.
Okay, can you see my screen? Full screen mode? Let's see. Is it on full screen mode now? Okay, so so good morning, good afternoon, or good evening. It's really a pleasure to present this guide to you together with Steve Ellison. But first of all, let me take this chance to thank Dr. Tang Lin Teo for the initiative and for organizing this event for us. I would like also to mention and to say thanks to all working group members that contributed to this guide, to the production of this guide. Okay, so I will start by discussing so the background, the motivation for investing in this topic, and then I will discuss a little bit how to quantify the performance of qualitative analysis. But first of all, let me discuss that we have two types of chemical analysis. So we have the quantifications, the measurements, and the qualitative analysis. We can use the word examinations to designate this type of analysis. And these two analyses are rather different. These two types of analysis are rather different, but they have some common concerns, I would say, some common goals. Regardless of the type of chemical analysis, the analysis results must be fit for the intended purpose. This means that they should be supported or based on adequate references, and they should be affected by an adequate uncertainty. And let's use the word uncertainty for that quantification of the reliability of the result. And I would say that ideally, together with the result, we should know the uncertainty associated with the result, or at least take that uncertainty into account in the results interpretation. And this is applicable both to measurements and qualitative analysis. Regarding the analytical method that is used to produce the results, this analytical method must be valid. And this means that the method must be applicable to an adequate diversity of analyzed items. So if we have items with different matrices, with different levels of the property that is being assessed, so the method must be applicable to this scope, and this method should be able to produce fit for purpose results in most of the situations. Okay, occasionally the method will not work properly, and this is why all the analysis should be checked together with the adequate quality control. Currently, so the international accreditation of tests, so the international understanding about the competence of labs to perform tests, as I would say, different views if the test is a measurement or a qualitative analysis. For measurements, labs should be able to evaluate and to report the measurement uncertainty. They have to do it in the customer request, that information, if it is relevant for the conformity assessment involved, okay? And even in some cases, in some countries, it is always mandatory to report uncertainty. But in any occasion, the lab should be able to take the uncertainty into account in the results interpretation. For instance, if a conformity assessment is involved, the lab should be able to understand how the uncertainty impacts on the conformity assessment and should be able to quantify the risk of false decisions. Occasionally, the regulation states that the uncertainty is not to be taken into account, and then we can skip that assessment. But at least we should know how the uncertainty can impact in the results interpretation. Regarding qualitative analysis, accreditation, international accreditation is not asking labs to evaluate results uncertainty, but they have to prove that the results are fit for the intended use. This means that accreditation suggests that labs should validate the analytical methods used, and they understand the validation concept, I would say, in a classical view of this term, where uncertainty is not included in the validation. I would say that a more updated understanding of the validation concept includes the uncertainty in the validation of the analytical method and the comparison of the uncertainty with a target value. EURACHEM, together with CITAC, decided to invest in this topic, in this guidance, through the working group on qualitative analysis. And these institutions decided to invest in this topic due to the relevance of qualitative analysis. We have many relevant socioeconomic interests and individual interests that depend on a qualitative analysis. And also because there is a lack of references to help labs in deciding if these qualitative analyses are fit for the intended use. And occasionally, these analyses are not fit for the purpose in hand. The quantification of this uncertainty of the quality of these analyses is more relevant, of course, when the false results rate is close to the maximum admissible level. In some cases, the analytical methods are so selective and the samples are so simple regarding the matrix that is not so relevant, that quantification. Like mentioned by Dr. Nordin, so in this guide, the qualitative analysis is defined as a classification according to a specified criteria, where the output of this analysis is this non-quantifiable nominal property value. And the guide discussed that we have two types of qualitative analysis: some based on a quantitative criteria. Typically, when you have an instrumental method of analysis and your classification depends on the comparison of the signal value with the threshold for that signal. This is an example of quantitative criteria. But in other cases, we have a qualitative criteria. So you decide about how to classify the tested item by a change of a color or a precipitation that is observed by adding a chemical. And this guidance should be able to discuss how we handle this type of qualitative analysis. So regarding the general scenario that labs face when they have to assess the quality of their qualitative analysis, typically we are in two situations. The lab, in some cases, needs to perform a qualitative analysis and have no indication from the customer or from a regulator about how to perform the analysis, which criteria should be used for the analysis, and we also the lab also is not getting any feedback about how good the qualitative analysis should be. So requirements for that analysis. In that case, the lab must select his own way, so must understand the purpose of the analysis and develop the methodology and define requirements for the quality of this analysis that meet the specific needs that must be handled through the analysis. In other situations that are highly regulated situations, I would say, we get from the regulator exactly information about how to perform the analysis, how to set the criteria for the identifications, and in that case, the lab just need to follow that way, and does not need to ask if that criteria or the methods have a fit for purpose performance, I would say. Regarding results uncertainty, the uncertainty is reported in a measurement and in a qualitative analysis in a rather different way. If we have a measurement, if we have a quantification, typically the result is reported as a confidence interval that should include the true value of or the conventional true value of the measurement with a non-probability. While in qualitative analysis, since we have this nominal property present, absent, from that class or not from that class, since we have this binary result, typically the uncertainty is reported as a metric that expresses the chance of that result being correct. And this can be through probability, likelihood, odds, like it will be discussed by Steve. And one important thing that we should discuss is that this metric should be statistically sound, and we can achieve that by making sure that the metric is quantified from adequate diversity and number of studied cases. So if the population of items to be analyzed is wide and diverse, we should assess the performance of our qualitative analysis in this diverse population. And what we get from all that work for this assessment is a quantitative indication of the quality of the qualitative analysis, this uncertainty, that allow us to understand if our analysis fit for that intended use, and to understand if we need to improve the analysis, and also can tell us how careful should we be in claiming, for instance, the presence of a substance in a matrix. In the next two slides, I will present the content of the EURACHEM CITAC guide. So this guide is divided in two parts. First part, we have some theory, and the second part, examples. In the first part, we have the forward, scope, introduction. It is discussed the type of qualitative analysis, and then we have something about how to assess the performance of the qualitative analysis. I will discuss a little bit on that, and then we have something about how to express, report the qualitative analysis results and conclusions and recommendations. So Steve will discuss in his first lecture section 4, 5, and 6, and then we have some examples, 6 examples from different analytical fields, and that try to explain how the theory can be applied to solve specific problems and to assess specific qualitative analysis. And we use these examples to explain some difficulties and some fragilities associated with some approaches to evaluate qualitative analysis. And then we have some annexes with some additional details for the theory and some bibliography. Let's go back to the type of qualitative analysis. So like I mentioned, we have two types of qualitative analysis mentioned in this guide. Qualitative analysis based on a qualitative criteria like changing a color. In the example that you have in the slide, you have the detection of aliphatic aldehydes in a solution by color change after addition of this shift reagent, or identification of crystalline form of a material by observation. Where for the quantitative criteria supporting a qualitative analysis, we have the identification of pesticide residues in fruits by GCMS, or assessing the spectral equivalence between a new and previously used raw material from the industry to check if they have some equivalence in the composition. This guide also mentions a third type of qualitative analysis. That is when you measure a quantity in your analyzed item, and then to compare the measured value with a maximum value for the measurement, and the outcome of that comparison will be claiming that the item is conform or not conform with that limit. This is somehow transforming a measurement in a qualitative analysis, transforming a measurement that is reported with uncertainty in a qualitative output, yes, no. And this guide is not discussing this type of conformity assessment in detail, because there is a EURACHEM CITAC guide on this topic, but in Annex B, it is discussed how can you use the metrics that are usually used to assess the performance of qualitative analysis. How can you use these metrics to describe the uncertainty of this type of conformity assessments? Okay, after defining how to perform the test, at least the experimental part of the test, how to perform sample preparation, how to perform the instrumental analysis, we have to decide by convention how to label results, if they are positive or negative. And this is rather arbitrary. Usually, in chemistry, a positive result is a result for the presence of a substance or for the match of an item in a specific class, and a negative is when that substance is not present or the item is not matching that class. If the substance is a forbidden substance, okay, the outcome of the result is not, I would say, very positive, but the result is considered positive regarding the analytical point of view. After this defining that convention, we have to assess the performance of our analytical method by calculating rates of true and false results. So in that case, we study positive and negative cases, real positives and real negative items, and then we check the chance of getting a correct or incorrect result from this analysis. And one important point that you have to discuss is that how rates are calculated can vary. You can calculate rates by taking the number of true and false results using as a base a specific type of case. So if total total number of positive or negative cases, a specific type of results, total number of positive or negative results, or the total number of all cases or all type of results. And this, the way you calculate rates, is very important because it affects the meaning of the rate. Only when total rate is calculated for a specific type of case, that rate will not depend on prevalence. It will not depend on the proportion of positive and negative cases that are being assessed. This is why we use it more in this guide. So probably the most popular way of reporting performance of qualitative analysis is through a contingency table. And this contingency table is typically a table where we have in columns cases and in lines the results. And let me give you a specific example of a contingency table. In this table, so we assessed 233 positive cases. So we have, in this case, we have items that we know that are positive. And we studied, we analyzed 233 positive cases there. And from this analysis, we got 228 positive results. So the true positive rate is 228 divided by 233, 97.8%. And the complementary value of that percentage is the false negative rates. That is 5 divided by 233. That are the cases where, although the case is positive, the output or the result is negative. So this is a false negative result. For the negative cases, it was studied 301 negative cases, and in only one occasion we got false positive. So the false positive rates is 0.33%. This table is very nice to report performance of our qualitative analysis. Not the best way to report on the uncertainty, on the quality of a specific test, like it will be mentioned in the following presentations. But we also need to discuss another important point associated with this contingency table, because the way cases, positive and negative cases are defined also vary. You can define a case as positive or negative by knowing the origin. So if you have a person that you know that has a specific illness, you know from a medical assessment of that person that person has that illness. If you want to test a screening method of this illness situation, so you take a sample, typically blood sample from that individual, you test it, and you will assess the ability of the test to confirm the illness situation or illness of that person. So, and in that case, the case is defined by knowing the source of that blood sample. We can also define a case by formulating. So if you take a lettuce sample, if you add a mass fraction of a pesticide above a concentration that should be detected, you get a positive case to run your validation. We can also define a case not by origin or formulation, but by using a more selective alternative classification method. For instance, if you have an immunoassay to identify pesticides, instead of spiking foods with a pesticide, you can run unknown food samples using a immunoassay and using a more selective method based on GCM-SMS, and you will define a positive and negative cases depending on the output of the GCM-SMS method. This works perfectly if the classification alternative method is much more selective than the one that is being assessed. But you can quantify your performance using reference data instead of the other sources of cases, I would say. So you can assess your algorithm, typically for an instrumental method of analysis, to identify properly your item by using signals data that from a reference that has a label that you know exactly if each data is positive or negative cases for your analysis. We'll discuss a little bit more about that. The other thing that is very important to discuss when we discuss the performance qualification of performance of this qualitative analysis is that we have some limitations on how to quantify the performance through experimentation. So if our analytical method is very selective, so has very low false result rates, we need a large number of tests to get reliable estimates of the performance of our qualitative analysis. In this slide, we have a table that explains us how this can be difficult to handle when we have a very selective analytical method. Imagine if we have a method with a false positive rate of 1%, you need to perform 299 analysis of negative cases. So this is a false positive, 1% of false positive. So you need to perform 299 analysis of negative cases to have a 95% chance of getting at least one false positive. And you need to perform 459 analysis of negative cases to be 99% sure that we will get at least one false positive. This means that we need lots of tests to check a specific false result rate. If you want to get reliable estimates of the false result rates, you need to multiply this number of tests by 5. So this means that if your analytical method is very selective, expensive, and time consuming, you will never assess the performance through experimentation exclusively. You can somehow overcome such limitation if your selectivity, if your method is not very selective. Imagine that if you decide that a false result rate, a false positive rate below 5% is okay. So what can you do? You perform the first 59 analysis of negative cases, and if you got no positive results, you can guess that no false positive results, you can guess that probably the false results rate is not larger than 5%, and then you start the analysis of your unknown samples, but you do it with extra confirmation of your analysis until you get more results from negative cases that will allow you to get a better and more sound quantification of false results rates. So, but like I mentioned, we can assess the performance by using a database. So if we want to avoid the costs of assessing the performance through experimentation exclusively, you can assess the performance typically of an instrumental method of analysis by getting a database with signals that you know that are from specific classes, And then you check your identification algorithm by comparing how your algorithm handles that signals. The strategy is nice to check your algorithm, but has a big problem. Typically the database is not a representative of the testing population. If you have a database of mass spectrum, you will have one mass spectrum of each substance, and usually in the tested population, you probably have some substances will appear more times than others, of course, and in this database you will have items or spectrums that of substances that are not really likely to be present in testing population. So this testing population is really not a representative of the real situation. So we should use this only as a first screening of the performance of our analytical method. One of the most promising, I would say, techniques to assess the performance of very selective qualitative analysis, if we have an instrumental method of analysis, is by simulating the signals. So if we are able to produce models of, imagine a blank signal of our instrumental method of analysis, we can simulate the chance that this blank signal will produce a signal that can be wrongly interpreted as from a positive case. And so we can by this simulation quantify false result rates. The only problem associated with this tool is that we must be really careful in modeling the signals, in checking the assumptions of the models, because if the models are not applicable, are not good description of the reality, the estimates will also be rather will be wrong. So let me close this this presentation with some remarks. So many qualitative analyses have a relevant socioeconomic impact. We really need to pay attention to this type of analysis, and some of them will for sure not be fit for the intended use. We can quantify in an objective way the performance of this analysis, but we have some problems, some limitations. If you want to handle these analysis or highly selective analysis only from experimentation, okay, in that case we will need to perform probably too many analyses in a way that this will not be economically feasible. This is why simulations can help us. So thank you very much for your attention.
Thank you, Ricardo. Thank you very much for your talk. And I believe the audience appreciates you taking time to explain the key messages from the EURACHEM CITAC guide. And it will take us some time to fully grasp the content of the guide and to implement it. But we look forward to hearing more examples from you and Steve later on. We have a number of questions, but Steve has kindly addressed them as you were talking. And we have exceeded the time by about 10 minutes. So if you're agreeable, we should move on to the next speaker. Steve, would that be all right?
Yes.
Oh, yes, there is a question that just popped up. What does very selective method mean? Could you explain? Maybe we just take this question.
Okay, so when they call it very selective, I would say that is a method where the false results rates are low. So so we can so the word or the term is rather general. I would say that it is a very selective method is to identify cocaine in purified cocaine using GCM-SMS. It will be extremely selective because we have high concentration of analytes. Since it is purified, the matrix will be almost irrelevant, and this is a rather easy analytical qualitative analysis. Was it useful, my reply?
Yes, I think it's very clear. We have another question, but I'm tempted to just put this to the end of the session where we have our Q&A from Puisi. Thank you, Ricardo.
Okay, thank you.
Okay, so now I shall introduce our third speaker, Dr. Stephen Ellison. Dr. Ellison is also a co-editor of the EURACHEM CITAC guide. He is the secretary of EURACHEM's Qualitative Analysis Working Group and is also a member of CITAC. Dr. Ellison is currently a science fellow with the LGC Limited in the United Kingdom. And today he will also deliver 2 topics for us. His first talk covers the expression of confidence in qualitative analysis. Steve, the screen is yours.
Thank you. Can I just check briefly how long I've got, since you said we might be running a little late?
We will reduce the break time for you.
That's a challenge. You should be able to see a title screen.
Yes, yes, I do.
That's great. Okay, well, that's my topic for today. I'm just going to talk mostly about the different ways of expressing confidence in qualitative analysis. So there's quite a long list of things to talk about, which is why I asked about how long I have. I'm going to talk a bit about basic response rates, true positive, false positive rates. And I'm going to break the different metrics down into 3 broad areas. One is what I would call performance of the test methods, so they're performance summaries. One is an index of performance in practice. Predictive values relate to how something performs in the real world. I'm going to talk a bit about cumulative probability because there are a couple of metrics, likelihood ratio and Bayesian posterior probability, which take into account prior information and can also take into account additional information as it arises. I'm then going to talk very briefly, I'm just going to introduce the possible reporting formats in the guide and say a little bit about what our guide says that we can reasonably expect from laboratories. I'll say straight away on that one, we're not going to insist, well, the guide does not tell you to do anything that an accreditation body doesn't tell you to do. We're rather more concerned with not overburdening laboratories or over-interpreting, but I will get to that right towards the end. So let's make a start on the basics. There's quite a long list of metrics in the guide. You'll find it in table. This is table 2 in the EURACHEM guide. I'm not going to talk about all of them today. I'm going to talk about a few of them in a bit more detail. The basic feature, though, is you'll see that they almost all are functions of these little things which are labeled things like TP, FN, and so on. They're true positive counts. And they come out of a table like this that Ricardo has already shown you with a bit more detail. So these lowercase, and nomenclature is lowercase means a count, uppercase means a rate or a probability. Now, I'm going to be talking about these tables quite a lot, and I don't want to put a whole table in, so I want something a bit more graphical. So I'm going to take a couple of graphical shortcuts. First, I'm going to color code the different parts of the table. So anything red is a positive case, a genuinely positive sample. For example, if these were people being tested for a disease, then the people who have the disease would be counted in this red column, and the people who do not would be counted in the blue column. So cases are color coded. Similarly, a sample that contains cocaine would be in the red column, one that doesn't would be in the blue column if you're testing for cocaine. The other shortcut I'm going to take is that a tick means a correct response, a correct result. So the results are down this side generally. So a positive result with a positive case is a correct result. A negative result with a negative case is a correct result. So that's my quick graphical coding. And later on, I'll also use the idea that maybe this size here is proportional to the number of items in each box. But let's start by talking about some of the simplest metrics. Now, the two most common performance metrics that are quoted, particularly in the clinical area, are sensitivity and specificity. They're in the top part of this table, which I've simplified a little bit. And you can see that sensitivity is essentially a true positive rate. Specificity is defined alternatively as a true negative rate. Now, the equations don't look very informative, so let's have a look at what they look like in pictures, I hope. So our true positive rate, our sensitivity, is a ratio of two different counts. So looking at our contingency table, you can see that it's the number of correct positive results divided by the total number of positive cases. Similarly, specificity is the total number of correct negative results divided by the total number of negative cases. Those are simple ratios as they stand. They're numbers, but they do have quite an important statistical meaning, and I'd like to explain that in a little bit of detail because the concepts matter later further on. They're both kinds of what's called conditional probability, and I need to explain what I mean by that. If you look at sensitivity as an example, it's a number divided by a total number. So it's a proportion, and if this is a sample, this is an estimate of probability. But the question I'm asking is, what probability exactly have we described here? Have we described, for example, the probability of getting a positive result? Well, yes, but only to an extent, because we're only talking about the part of the contingency table that covers positive cases. So we're talking about a probability that relates to positive cases only. And that is what we mean by a conditional probability. The condition is we're talking about positive cases, samples that contain a drug, people that have a disease. We're not talking about the right-hand half of the table at all. So we're actually talking about a small part, of maybe a large part, but only a part of our complete sample space. And there's a nomenclature for that, which looks like this. It's a probability of a positive observation. Here we go, that's the ratio, given a positive case. And this part on the right tells us which part of our sample set we're looking at. And this says we're looking at positive cases only. And this is what a conditional probability does. It tells us about a probability when we're talking about only part of the population. And we're going to need conditional probability later, but if we look at what sensitivity and specificity are actually telling us in terms of probability, both of them are talking about our conditional probabilities depending on a particular type of case. So sensitivity is a probability of a positive result given that we're talking about positive cases. And specificity is almost exactly the opposite of that. It's the probability of a negative result, a correct result, of course, when we're only talking about negative cases. That's what conditional probability does. It tells us which part of the sample space we're talking about. So conditional probability is nearly always higher than otherwise, but the most important part is that it's only talking about part of the data. Now, there's another interesting feature of that. Because we're only talking about positive cases for sensitivity, it doesn't matter how many negative cases our data set contained. We're not interested. That will not change our estimate of sensitivity, except by changing the uncertainty of the proportion. But we can have 5 or 50 or 5,000 negative cases, and we would still have exactly the same result here if we still only had, let's say, 100 positive cases. And exactly the same is true of specificity. So these two, sensitivity and specificity, are interesting in that they don't depend on the relative number of positive and negative cases. So that means that both of them are talking solely about method performance. They're only talking about the test set, the test method given for example, a positive case. They're not telling us about the probability that we'll get a positive result in the population at large. They're not telling us about the probability that all results are correct. They're telling us about the probability that we'll get a positive result from a positive case. And that's a feature of the test method generally. So these two are quite useful ways of summarizing the qualitative performance of test methods. Of course, that isn't a complete statement of confidence. So there are other metrics in the world. We've got two predictive values, positive and negative predictive value in the table. And let's talk a little bit about what those are. Going back to our graphical presentation again, our positive predictive value, and I'm only going to talk about one for the moment. It's got the same number on the top line. It's the number of correct positive cases, correct positive results, I beg your pardon. So it's the same as our true positive rate on the top line, but the bottom line is quite different. The bottom line is the sum of the top two cells of the contingency table. So this is the total number of positive results. So this is a correct positive result, and this is an incorrect positive result, a false positive. Now, what's that telling us? Again, in terms of conditional probability, I've said we're only talking about the top part of the table, and that's about our observed values, our observed positive results. So we know that as a conditional probability, it's a proportion of positive observations. So the right-hand half of our condition, the actual condition, is we're talking about positive results. So which proportion is it? Well, it's a proportion of positive cases among all of this set. The thing that's different about this is that the case type is different. So it's the proportion of positive cases among our positive observations. So it's the probability of a positive case given a positive observation. And that's quite an important thing to know, because it's telling us something about how reliable a positive result is. And those of you who have noticed all of the lateral flow testing in COVID recently, over the last year particularly, will know that lateral flow tests are quite sensitive and quite specific, but the predictive value can actually be quite poor. And there's a reason for that, and it's tied up with the fact that unlike sensitivity and specificity, we're not just talking about positive cases. Let's have a closer look. I'm going to change my graphical presentation a little bit, and I'm going to say that the size of this box, the width of the box, is proportional to the number of cases in the box. So this is a large number of people with COVID, or people with a disease, or samples with a regulated substance in. And the vertical scale is about the number of results, the number of observations we've got, positive or negative observations. Now, if we redraw that, we can draw two different cases. Here's a case where we've got a lot of positive observations, a lot of true positives, but we've also got a lot of positive cases compared to negative cases. So this is, if you like, a lot of samples that contain a regulated substance and a few samples that don't in a population. Now, if we've got a reasonably sensitive test, it'll always respond to our drug, so we get a lot of positive results. And if it's reasonably specific, we won't have many here. But the important thing is that this situation with a lot of positive true cases gives us a high positive predictive value. If we have not very many positive cases, then fairly obviously our ratio is going to be lower, because we've got a smaller number on the top line and the same number on the bottom line. But there's a really important thing about this. Looking at the vertical scale, the number of positive results in each case is identical. So what we've got is the same number of results, but same number of positive results. But because the number of cases is different, we've got a different positive predictive value. And that tells us that although we're being told something that is really important to know, if we get a positive result, do we have COVID? Or worse, if we have a negative result, can we go to work without infecting anybody? Positive predictive value tells us the answer to that question. How sure can we be that we are free from a disease, or that we have no drugs in a sample? The problem is that our validation data set will give us a particular value, because going back a stage, we've chosen the number of cases, but we may not have the same proportions of positive and negative true cases in a real population. And what happens in the case of COVID at low prevalence is that our positive predictive value degrades because there's a larger proportion of false positives in our total set of positives. In other words, when we're talking about positive predictive value from validation data, that may not apply to a real population in practice. I'll get round to, well, the next topic covers how we can address that. This is to do with posterior probability and likelihood, and to do that, I'm going to have to talk a little bit about Bayes. So we're moving into the bottom part of our table. Let's say that we've got a validation study where we've got, let's say, 100 positive test samples and 100 negative test samples. But we know the answers for these. We know they're positive and we know they're negative. And we've got a number of positive results in our positive cases and a much smaller number in our negative cases and so on. So this is kind of what we would like a validation contingency table to look like. We expect to have a large number of correct positive results, and we expect to have a large number of correct negative results, and the other two are quite small. So that's our validation study. We can get sort of probabilities out of this. At least we can get sensitivity and specificity out of this. But we also know that we've got a population of test samples that has a very different balance between positive cases and negative cases. And this might be a disease, or it might be test samples of white powder taken from supermarkets or something like that. And of course, it might be exactly the other way around. And there are circumstances where a population can have a very large number of positive samples. The sad one is prison populations for urine testing. But this might be something like urine testing for drugs in an ordinary workplace where you don't expect many people to be positive for the drugs. Now, we've got two pieces of information. First, we've got something about the performance of our method, and second, we've got something about the probability of getting a positive result without doing any measurements. So what can we do with that? How do we take account of both of those pieces of information in coming to a conclusion? Now, let's have a look at the color change here is just that I'm going to be focusing on the positives here, on the correct results. What we'd like to know is what are these things, a positive result, what's that telling us about our test sample? Now, the information we've got from our validation is we've got our sensitivity, which is a conditional probability. It's the probability of getting a positive result from a positive case. It's good if that's high. From our population, we've got the probability that we've got a positive case. Now, the nice thing is that all we need to do, we know, if you remember, that this particular proportion, this probability sensitivity here, is a conditional probability. It doesn't care about how many negative results there are. It doesn't care how many positive results there are. The probability is fixed. So we can take that probability and we can apply it to this population probability to give us a combined probability that we'll get a positive case in our true positive result in our population at large. So we've just got a combination here of the probability of positive cases multiplied by a conditional probability. And those of you who are familiar with Bayes will know that we're halfway there. We've also got the probability of negative results and so on. So we can start saying things about whether at our false positive rates. So we can also say that if we've got negative results, we can give an idea. Sorry, we've got a lot of negative cases. That's the size of this blue part here. We can say something about the number or the probability of seeing what this would be a false positive. Now that's enough for us to answer a really important question. If you remember correctly, our positive predictive value is based on the sum of these two top rows of the table, the number of positive results we get. So if we want to know what's the probability of a positive case, given that we've got a positive observation, in our population as a whole, we've got the probability of a positive case from a positive sample, which we've calculated on the previous slide. And we need to divide that by the total number in these two boxes. And that is a bit intricate, but it's basically the two equations that we had on the previous slide. Now, what we're looking at here is actually Bayes' formula, Bayes' theorem. We've got the bits from our previous slide, and this formula is Bayes' theorem. And you'll see that what we've calculated is the probability essentially that a positive result means a positive case. What's the probability that we've got the disease if we test positive? And we can calculate that if we know the opposite probability. What's the probability of a result if we're positive? So that's how we convert things we know from the test method into things we can say about the population and about an individual sample. So Bayes' formula gives us a way of combining information to give us a conclusion about the probability of a particular outcome given a test result. And that gives us a direct measure of confidence in the qualitative result. It says, if we've got a positive test for a drug, we are 95% certain that that drug is present. Now, another aspect that I'm going to have to go through quite quickly, there's a whole annex in the EURACHEM guide on this, is something called likelihood ratio. And this is another way of looking at what our test result is telling us about the test material. To explain likelihood ratio, I have to introduce a different way of talking about probability. Most of you have at least seen horse racing and betting, where everybody talks about odds. Who's the odds-on favourite? Well, odds are just another way of talking about probability. And the odds in favour of an event are just the probability of it happening divided by the probability of it not happening. It happens, and there is a derivation given in the EURACHEM guide, that you can write the whole of Bayes' formula in odds form. And what we can then say is that we've got what's called posterior odds. If we've got a piece of evidence, such as a positive result, and a question that we're asking, like, is the test sample truly positive? We can answer that question starting with the prior probability that we get a positive case, and then we can look at the probability that we get a positive result from a positive case divided by the probability that we get a negative result from a positive case. And these are all things that we can get out of our contingency table. So those things, I should say, come out of the contingency table. This is something that we know about the population, or that we know before we've done the test. In words, posterior odds are the prior odds times the likelihood ratio. So this thing here, that little ratio there, that's the likelihood ratio. It's important because first it tells us the change in odds that are due to a test result. So it tells us something about the extra information added by a test result. It's convenient in one respect because if we have multiple independent test results, for example, we have a mass spectrometric follow-up to an immunoassay screening method, we can combine likelihood ratios simply by multiplying them. So that's useful. But really importantly, likelihood ratio itself, the likelihood ratio here, is the part of this equation that is not about the prior probability. So if we just talk about this, we're only talking about what the test is telling us. We don't need to talk about the population. And that's quite important in some circumstances, like forensic cases, where we can't make an assumption about the prior probability. There is an interpretation, unlike probabilities, likelihood ratios can be anywhere between 0 and infinity. They're mostly not either 0 or infinity, but you can get some pretty big numbers. So here's a way of interpreting likelihood ratios in words that's recommended by the European Network of Forensic Science Institutes. So you can see that likelihood ratios of 2 to 10 not very strong in forensic terms. Likelihood ratios down here, perhaps up into the thousands, are the sort of likelihood ratio we might get from some paternity tests, where you're trying to find out the paternity of a child, and you've got perhaps two prospective fathers, or one prospective father who has denied fathering the child in order to get out of paying child support. And because of the way DNA works, essentially, the likelihood ratios for that this person is the father versus some other person is the father, can be quite low. That's because a parent only donates half their DNA to a child. DNA fingerprinting is nearly always way above 1 million if you're looking for chance match probabilities. One thing I should say, all of these say findings for one proposition relative to an alternative. And to give you an example in DNA forensics, the proposition is the profile came from that person, the defendant, and the alternative is nearly always the sample came from a random person, a person chosen at random from the general population. So the two hypotheses that are compared there are that person versus a person chosen at random. For drug identification, it would be one hypothesis is that it's cocaine. The alternate might be it's not a controlled drug or it's another substance. So likelihood ratios, in practice, it's a useful weight of evidence metric. It tells you what your test method has told you, what your test result is telling you, without using the prior probability, which makes it very useful in forensic applications because we're simply not allowed to assume anything about guilt or innocence. That's my tour of the table of metrics. I'd just like to quickly show some possible verbal reporting formats. These are straight from the guide itself, so you can have a look at the guide and look at the context. But for example, if we've got sensitivity and specificity, you might accompany the result with some information on the test reliability. Sensitivity and specificity might help a physician judge how reliable this result might be. And there's a lovely comment in the chat at the moment from Bryn Hibbert relating to tuberculosis tests, which are, again, very good specificity, but actually the positive predictive value not so great because of the number of negative cases. If we were looking at likelihood ratio, those might be, you might actually give the likelihood ratio. I think in forensic work, it is better practice to give the likelihood ratio and a verbal interpretation. And I'll be talking about an example later where it's also considered good practice in the forensic world to give an indication of the scale you're reporting on. So telling a jury or a person, a lay person, that you've got very strong evidence. It does help if you say, and by very strong, I'm on a scale that goes from weak, strong, very strong, extremely strong, compelling, something like that, so that they know roughly where you are, whether you're saying the strongest evidence you'll ever see or something partway along the scale. And finally, there's an example here with a posterior probability. So this one's quite wordy. It says we've got gasoline residues in fire debris with a posterior probability of 99.998%. That's obviously quite high. And it says how that probability was estimated. So those are just suggestions of how you might report if you wanted to. Now, I say if you wanted to, because there are some important limitations and that I'd like to mention. First, it's actually quite hard to estimate low false response rates. A 1% false response rate takes about 300 tests just to be sure of finding one positive, one false response. So very often we're not going to be very sure about the actual rate. It can be very hard to estimate population probabilities. So we don't often have prior probabilities to work with that are reliable. We might have exactly, someone has asked, how do you get reliable information about prevalence of a case? I'm afraid the only answer to that is what we're doing in the UK at the moment for COVID. We've got a regular sampling exercise, which takes about 1,500 people a week, asks them to do a test and checks whether their results are genuinely positive using PCR. That's expensive, but it gives us a fairly good indication about the prevalence of a disease. It's much more difficult, for example, if you're handed a white powder and you want to estimate the prevalence of cocaine in white powder. It depends hugely on where that powder came from. And the fact that it's been handed to you by someone in a blue uniform can make a very big difference to what you think is the probability of it being a regulated substance. But it can be very hard to do that. And that's another reason why we might stay away from posterior probabilities, because we can't get the prior probability, the prevalence information. We've got an example tomorrow which relates to spectroscopy, which talks about how likely it is that you see two different peaks in a spectrum. They're not independent, and joint probabilities can make a huge difference if you're combining probabilities, orders of magnitude difference sometimes. So quite a lot of these numbers can be hard to estimate, and that's why we've got some of the recommendations in the guide that we have. And this is my final slide. What we think is we can reasonably expect to see in laboratories. Now, if you're an accredited laboratory and you're doing qualitative analysis, you'll already be doing the first thing. Conditions of testing will be under control. For example, your reagents will be from reputable suppliers, your reagent concentrations will be measured using calibrated equipment and so on. And that's always important for quality in qualitative testing. The conditions of the test should be under control, and all of those are, when you're doing things like temperatures, volumes, reagent concentrations, they are SI traceable quantities that can be measured, and you can expect to see those properly controlled in an analytical laboratory. The guide says that it would be important for laboratories to check at least the most critical false response rate. So, for example, if you're doing screening, it's important, and you're going to take action on positive results, it's important to have an idea of the false positive rate, at least. Better, of course, to have an idea of both false response rates. So ideally, try and monitor using perhaps check samples that you know are positive and so on, to keep an eye on whether you start to see unexpected failures. There's a, if you like, what I would call a no-brainer. If there is a code of best practice in your area of work, please follow it. And there's one right at the end that's really important, because it's, if you like, a negative recommendation. We don't really think that it's sensible for routine testing labs to be reporting quantitative uncertainties for qualitative analysis at the moment. It's actually very difficult to do, and it's not clear what end users are going to do with them at the moment. There's a need to have sufficient confidence based on your response rates, your sensitivity and specificity. That's what you're responsible for. It's a different matter entirely to be looking at population probabilities and prevalence and making judgments there, unless, of course, you've got the infrastructure to support that. There are a few cases where you have, and in DNA fingerprinting is one of them. In the UK, at least, we do have all the population probabilities that we need from sampling databases designed for that purpose. So we've got the prior probabilities and so on. But in most circumstances, that information is not available, and it's really quite difficult to obtain it. And we don't think that it's sensible to make guesses. And that's where I'm going to stop. So thank you all very much for your attention. And thank you again to Tanglin and all of her colleagues for a really well organized event.
Thank you. Thanks, Steve, very much for your comprehensive talk. And the illustrations have been very useful in helping us understand the concepts. And thanks for taking the questions along the way. You have promptly ended your talk at the beginning of the next talk. So we do not have a break, I'm afraid. So Ricardo, would you be happy to continue with your second talk of the day?
Yes, okay. I will do that. Let me get the file. Okay, so now we will have some examples, some application examples of the theory. Okay. Sorry, my screen is split. Can you see the full screen mode now?
Yes, thanks.
Okay, so in this presentation, I will describe the fifth example of the EURACHEM CITAC guide. I will start with a brief introduction, and then I will discuss the validation approach, present some results, and finish with some final remarks. This example describes how to assess the performance of the identification of trace levels of compounds in complex matrices by GCM-SMS, which is a very selective instrumental method of analysis for many applications. And in this type of identification, typically you support your result from analyte retention time. Sometimes you use the relative retention time, and we also use the mass spectrum information, typically the ratio of the abundance of characteristic fragments, to support your identification. In this case, a positive result is a result where the presence of the analyte is confirmed or considered. And in this example, I will discuss how to support or how to define identification criteria from the observed variability of these identification parameters. And I will present you the results of the determination of chlorpyrifos methyl residues in foodstuffs of vegetable origin from example E5. In this example, we also have data from malathion, but I decided to skip to make this presentation shorter. Okay, first the validation. Before starting the validation, we must have defined the analytical method, so how sample is prepared, the instrumental conditions, and we also have to specify the characteristic fragments that are used for the identification. Then you need to quantify the performance of retention time. You need to quantify the performance, the variability of abundance ratios, and then we have to understand how retention time together with abundance ratios are able to produce the identification. So we have to quantify the performance of the identification based on both retention time and then abundance ratios. And very importantly, very important for us, we have to finish the validation by deciding if the performance observed in that validation stage, if the performance is fit for the intended use. Let's start by discussing how can we validate retention times. How can we set criteria for retention times, and how can we assess the performance of retention times for the identification? First of all, we must decide about the distribution type of retention time. I would say that in most of the cases, retention time will have a normal distribution. We can check this assumption easily, but after checking it, we can start collecting information about the dispersion of that retention time. How do we do that? Typically, we perform replicate determination of retention times under repeatability conditions. So we have several samples. We get several samples. We take replicate injections of sample extracts, and we get information about the variability of retention times in the same conditions. And we collect that information from different samples, and we pool them in this pooled standard deviation that somehow allow us to pool repeatability standard deviation for retention times from low degrees of freedom from many samples, to pool them in a repeatability standard deviation that will get more degrees of freedoms by the pooling that information. And why do you need that? We need that because we will use it for as an identification criteria. So by knowing the precision of retention time, we can say that two retention times from the same analyte should have an absolute value of the difference smaller than the t-value of the t-distribution for the relevant degrees of freedom, and the studied or the defined confidence level, in this case 99.9%, times square root of 2 times the standard deviation that was previously calculated. So this means that if a peak from our sample, retention time from our sample, differs in relation to the retention time of the analyte observed in a calibrator less than this term, we suspect that that peak from the sample can be from the analyte. In this case, the confidence level is 99.9% because we want to reduce the rate of false negatives very much. And I must highlight that the retention times that are compared here from the analyte, from the calibrator, and from the peak of the sample, the size of the peaks must have deviation differences below 20%, because we know that the size of the peak affects retention time. And what can we conclude from this process? So we can conclude that for the identification of compounds based on retention time, the true the true positive rate is 99.9% because this was the confidence level defined for that identification criteria. And we also need the false positives to get the likelihood ratio, okay, afterwards. And the false positive was set as 10% because we know that there is a 10% chance of having a peak not from the analyte, but closer to the retention time of the analyte, less than that criteria for the agreement of retention times. And this somehow characterizes the performance of using retention time for identification. Okay, but identification relies also on mass spectrum, and in this case we will use the ion abundance ratios. Here the situation is a little more complex because we know that the abundance ratio can have a distribution that deviates from normality. We know from statistics that the ratio of two correlated variables can have a distribution that deviates from normality, and you have somehow to handle this. And first, we have to know what is the dispersion correlation between abundance ratios, and what we do. We do some replicate analysis of samples extracts without the analyte, so negative cases, and with the analyte, spiked analyte, that are our positive cases that are being tested. So we do replicate injections of extracts with and without the analyte, and then we calculate the mean, the standard deviation, and correlation between the abundance of both fragments that are mentioned in this example. And why do we need that? We need that because by knowing the mean value, standard deviation, and correlation of these values, we can simulate the ratio. And we use the Monte Carlo method simulation. Sounds complex, but it's rather trivial to implement that in an Excel file. And then so we use this Excel file to simulate what will be the distribution of the ratio of that abundance with that mean value, with that dispersion, and with that correlation. If we take spiked samples values, we can simulate the distribution of the ratio of these correlated abundances, and then by taking the 100,000 simulated values, we can take the first and the 99th percentile and define confidence limits for the acceptance of these abundance ratios for 98% confidence level. Regarding the negative cases, so the data from the extracts without the analyte, what we do, we take the mean signal noise, the standard deviation of the signal noise, and we simulate, we model, we define models of the signal noise, but in this case we use normal distribution truncated below zero because we do not expect negative areas, and this simulates our signal noise. Okay, and this means that regarding the use of ion abundance for identification, we can say that so the true positive of these identification based on this parameter are 98%, because this is the confidence level that we use to define the limits, the acceptance limits for abundance ratios. But the false positives, how do we get the false positives? The false positives, we get them through simulation. So we simulate the signal noise 7,000 times, and we check how many signal noises will get abundance that are compatible with the studied concentration level, because the false positive is estimated at different concentration levels. So we check what is the chance of, by chance, the noise producing abundance compatible with concentration level of that analyte, and by chance get a ratio that meets the confidence interval that was defined from spiked samples. So we calculate what is the chance that the noise will produce intense signals, as intense as expected for that concentration, and with the ratio that meets the abundance ratio criteria. And let me give you now examples or the data that was obtained for the chlorpyrifos material analysis. So we have here, it were analyzed 3 extracts that were spiked at different mass fractions. So the qualitative analysis performance was assessed at different mass fraction values. And then we have other extracts with not detectable chlorpyrifos material levels that were used to model the signal noise. Here we have the mean retention time. More importantly, the standard deviation of retention time repeatability, and then for the abundance of the ions, we have the 2 characteristic ions that were considered for chlorpyrifos material. We have the mean abundance, the standard deviation of the abundance of this fragment. For the other fragment, mean abundance, standard deviation, and the correlation of the abundance between these 2 fragments to understand the correlation between these 2 values. And you can see that we have different correlations, different mean values, and different dispersions as the concentration varies. Okay, we have different values for our simulation, and we use that to define the confidence limits for the edification parameters. So we conclude that for our spiked extracts and for mass fractions between 0.04 and 3.33 that milliamps per kilogram, that were the studied mass fractions. So the maximum tolerance for the agreement between the retention times that was considered is 0.18 for 99.9% confidence level, and the tolerance limits, confidence limits for abundance ratios for 98% confidence level is 0.439 to 1.18. And let me continue. Now the performance of this qualitative analysis is summarized in this table. What we have here, so analyze chlorpyrifos methyl. We have true positive rates, false positives, likelihood for positive results, that is the ratio between true positives and false positives. And then we have this posterior probability, assuming that the positive and negative results are equally likely. Okay, and this posterior probability, since results are equally likely, is likelihood ratio divided by likelihood ratio plus 1. And we have performance at different mass fraction. The first mass fraction is the limit of detection. Limit of detection defined only looking to the quantitative performance. Okay. And the third is limit of quantification, only looking to the performance of the measurement. And so what can we see? So for retention time, true positive 99.9%. This was the confidence for that tolerance. False positives 10%. That gives likelihood ratios of this value, and the posterior probability, that one. For abundance ratios, true positives 98, the same regardless of the mass fraction. False positives 30%, close to limit of detection, and then goes very low around limit of quantification. Likelihood ratio get these numbers, and the posterior probability these ones. If we identify based on both the retention time and abundance ratios, we know that these true positives multiply. The true positive rate will be 97.9. False positives will be these numbers that drives to likelihood ratios like this one and these posterior probabilities. So if we use the same criteria that was mentioned by Steve for forensic analysis, we can say that only above the limit of quantification, the likelihood ratio will be larger than 100,000, which is considered a very strong piece of evidence of the presence of the analyte. So, and by through simulation, we're able to quantify the false positive results rates and to understand how good can be our qualitative analysis. So this is an example that illustrates how highly selective instrumental methods of analysis can be assessed, or can be assessed their performance by simulation, by using the Monte Carlo method based on the distribution of the different identification parameters. Thank you for your attention.
Thank you, Ricardo, for your very, very detailed explanation. We have a simple question relating to the detection. Did you use SIM or full scan mode for the validation or for the example?
So in this case, use ITD. It was full scan mode.
Okay. And second question from Mrs. Tipaya. What number of replicates for qualitative analysis should we carry on for validation of methods and represent for standard deviation of each concentration?
So for this validation, it was around 20 replicates, because we take into account the number of degrees of freedom in the simulation. So if we have more replicates, it will improve your estimates because degrees of freedoms are considered in that model. But you should not be too few, because it will affect your estimates.
Okay, thanks, Ricardo. There's a question from me. In your presentation, you have given examples where the data is collected under repeatability conditions. Can we use data that are collected over different times, like under intermediate precision conditions?
In retention time, typically you prefer to manage repeatability conditions, because you identify your compound by comparing retention time from your sample, and we compare it with a calibrated that was injected in the same day, so in a short time scale. Yes. So it is better to do it. You can always manage retention time under intermediate precision conditions by identifying your compound by comparing retention time of your compound with retention time observed in another day. But then you will lose. You will work in more dispersal, or the dispersion of retention time will be larger and will not be so good for identification.
Right, thank you. One more question from Francesca. Is there a criterion to decide the concentration levels tested?
Okay, in this example, we study the concentration levels that, according to legislation, should be identifiable, I would say. So in pesticide residues in foodstuffs, you have some commodities where the use of the pesticide is forbidden, and there is the lowest determination level for this analysis. So we started from there, and it was clear that if we move a little bit from that concentration, then the performance improves much better. And so we just need to assess the performance close to the lower concentration levels.
Okay, thanks for taking so many questions. Thank you very much again, Ricardo. We will move on to the last talk for today. Yeah, Steve, over to you again.
Thank you. So, see if we can keep a little better to time this time. This is another example of deriving performance metrics from information available. The example is actually in the EURACHEM guide. So I'm going to try and zip through fairly quickly to give you a flavor of the estimates used. You can take a look at the EURACHEM guide for a little bit more detail and some alternative calculations. The qualitative analysis is testing for drugs using enzyme multiplied immunoassay. It relies on a color change above a threshold. It's testing in urine. It's a set of tests that are for a variety of controlled substances. I'm just going to talk about cocaine information today. Perhaps the most important thing is that the information source is primarily a database that was assembled in the literature, and we've got summary information from that. So we're looking at published detection probabilities as the main source of information on both method performance and the prevalence of drugs in a particular sample population. And I'm going to talk about deriving a likelihood ratio and posterior probability. So the kind of thing that you might want to provide in forensic reporting or workplace urine testing. EMIT itself, many of you will know, relies on starting with enzymes bound to a particular target, so an antigen, in this case, something very like cocaine, sufficiently like it so that antibodies for cocaine can bind to the antigen. And in doing so, they block the active site for the enzyme. And you have a substrate which will eventually change color given the chance. When you add your antigen, your substance, what happens is that some of these antibodies bind to your free drug in this case, and that leaves you with some unimpeded active sites for the enzyme, and that allows the enzyme to act on the substrate and generally generate a color change. And that, once you've got free enzyme, you can convert a lot of substrate quite quickly, and that means that you get a very sensitive test. You don't have to free up an awful lot of enzyme to get a lot of substrate change in color, and that makes it relatively easy to detect a color change. So what we've got is a test that can generate a color change with relatively small amounts of added drug substance. Now, the information we've got in the example, in fact, we've got three principal items of information. We've got a false positive rate and a false negative rate for the test method, and we've got a prevalence for cocaine. It's quite high at 0.2, and I'll come back to that when I talk about the relevance of the population. For this example, I'm going to be talking about some of the summary results that relate to the interpretation of the test result, so likelihood ratio or posterior probability. Let's start with likelihood ratio. Our likelihood ratio is a true positive rate divided by a false positive rate, and the reason for that is hiding in the EURACHEM guide, but they are conditional probabilities that relate directly to the conditional probabilities of finding something and finding something when it's not there, that I presented earlier. Now, our initial table only had the false positive rate, but the true positive rate and the true negative rate can be deduced directly from those by subtraction. And the false positive rate is 1 minus the true positive rate, if I remember correctly, the other way around. So effectively, we're using figures from the table to construct our likelihood ratio. And in this particular case, it's a fairly simple calculation. We've got 2 numbers, top and bottom, and we get a likelihood ratio of around 249. If you remember our forensic interpretation table, that puts us in moderately strong support. So our positive test result gives us moderately strong support on this reporting scale for the chance that cocaine is present rather than something else. And I'll get back again to exactly what else when I talk about reporting these results. So the likelihood ratio is relatively straightforward. It comes out of false response rates. The posterior probability is a bit more difficult because we have our Bayes formula. So we need our probability of positive cases, which is then multiplied by our probability of getting a positive result given a positive case. And we need to divide that by the total, the combined probability of getting any positive case. And that's Bayes' formula as I presented it earlier. So what we're looking for in this particular example is a probability that a sample contains cocaine given a positive result. Now, we've got some of the information in the table for our probability of a positive because we've got the true and false positive rates. I might have those the wrong way around actually, but it doesn't make a big difference. So we've got our combined probability of a positive, or at least some of it. We've definitely got the prevalence of cocaine in our population. We've definitely got our true positive rate. That's the chance of a positive result given that cocaine is actually present. Our probability of a positive result, I was a bit simplistic before, that's actually a calculation from other parts of the table. It involves the probability that cocaine is present, and fortunately we have the probability that it's not present, as these two are directly related. One is 1 minus the other. So we've got enough information in the table for this part of our combined probability of a positive result. We've got our true positive rate over there, and we've got our false positive rate up here. Once we've got that, we can just plug numbers into our equation. So we've got our probability of a positive result over the population, which is 0.2, just over 0.2 in fact. So if we plug those numbers back into our Bayes formula, we get a posterior probability that a sample contains cocaine of about 98% if we get a positive result. So this is telling us how confident we can be that a positive result means that we've got cocaine in the sample. And I guess the main thing there is we didn't need an awful lot of information to do that. We can actually get it out of the 2 false response rates and the prevalence. Reporting these, I've given a fairly wordy forensic witness statement like summary for the likelihood ratio. And this is the kind of statement that we would have given in the UK if we were using a likelihood ratio in DNA evidence. So we had a likelihood ratio of about 249, near 250, and that says we now have moderately strong support for our hypothesis. And the main hypothesis is the material is cocaine, and the alternative is that it's, and this is where the alternative is important, it's another controlled substance, because the database we're looking at is a database of positive samples that were tested for controlled substances. So the probabilities that we were looking at were probabilities that a controlled substance positive urine sample contained cocaine. So we're pretty sure we've got moderately strong support for the idea that our sample contains cocaine and not another controlled substance. And the scale we're reporting is from none to extremely strong, and you can see our moderately strong is somewhere in the middle of that range. So for a jury, for a lay audience, you can see that this is not very far up the scale, but is a good bit better than weak. So this is the kind of common sense wording that a jury is expected to be able to interpret. For the posterior probability, it's rather simpler. The probability that the material is cocaine rather than another controlled substance is approximately 98%. And I've just rounded that down a little bit. Let's talk about some limitations of this. The most important one is that the posterior probability in particular, but also the other method performance information are all directly relevant to the population we're talking about. In other words, that our true and false response rates represent what happens in our laboratory, and that's something that we might want to validate by looking at known positive and negative controls over a period of time. Much more likely is that we may see a difference between the database collection of information and a sample population of test materials. The thing that strikes me about this example is that cocaine isn't that common in urine for most people. So if you've got a prevalence of 20% that's in the database, that implies that the data came from known or probable positive samples, at least samples that are likely to test positive for a controlled substance. That doesn't make any difference to the likelihood ratio, because the likelihood ratio is effectively telling us what our result is, what information our result is adding. So in a sense, after the test, it's kind of 250 times more likely that the sample contains cocaine than it was before we did the test. So that's the kind of interpretation of likelihood ratio, but it doesn't tell you how likely it was before the test. The important thing is that if this is not representative of our target population, as I said, workplace testing is quite common, and 0.2 would be very high for workplace testing, then our posterior probability could be a very long way adrift. So we would need to be very careful of reporting posterior probabilities unless we were quite sure that our database matched our intended population. Now, in a clinical context, it almost certainly would. In some of the controlled substance testing, it depends whether it's a validation data set or a test at random from the population that would be generally sampled. Concluding remarks, we don't need a lot of information to get useful information, useful summary information, useful performance metrics, so we can get likelihood ratios and, to an extent, posterior probabilities, given only the false response rates and the prevalence. So we don't need a large number of pieces of information for this, but we do need to be careful that our prevalence information is relevant and that our performance is relevant to what's going on in our laboratory. And that's it. Thank you very much again for your attention.
Thank you, Steve. Yeah, prior to your talk, this talk, there is a question regarding the COVID-19 rapid test. I think it's related to what you mentioned at the end of your first talk. So how do you interpret sensitivity and specificity values that appears in the leaflets of the ART kits?
Well, assuming that they follow the usual convention in the laboratory medicine area, they'll have the same interpretation that we talked about in the first set of my first talk. So sensitivity is if you've got a positive case, a positive sample, it's the probability that you'll get a positive result from a positive sample. Similarly, specificity is the probability that you'll get a negative result from a negative sample. Those are straightforward. The difficulty is that those are derived from known samples that we know either contain or do not contain, well, depending on the test, but usually lateral flow, so viral protein. Why you need to be careful about interpreting that in practical use is that in practical use, lots of things can go wrong. If you get a positive sample, if you are positive for COVID, your first job is to get a good sample into your test kit. If you fail to do that, and this is particularly relevant for home testing and self-testing, poor sampling practice will mean that you miss COVID. So the actual sensitivity that you'll see in the field may be quite different to what you'll see in the laboratory. Now, I don't know, because I don't do tests on, we don't do the validation for COVID-19 lateral flow testing. I don't know whether the sensitivity that's reported is for known positive samples that are known to contain viral protein, or for known positive patients who've tested themselves. And I think it's usually for the former, because that's about the only thing that the test kit manufacturer can guarantee. So usually you do that on test materials that you know about. We've also talked about the fact that at low prevalence, a positive may be much more likely to be a false positive, simply because if you've got one patient in 10,000 with COVID and you've got a 1% false positive rate, that means something like 100 times the chance of a false positive compared to a true positive in your population, because there's such a big disparity between the number of true and false positive, positive and negative cases. So the information on the test kit is almost certainly about the performance of the test on good samples. You have to think a bit more about the population and the sampling methods in order to tell you what that means in practice in the field. So that's my answer to the question.
Thanks. Okay, so I think we have to now bring everyone to the question and answer session, which actually we would like to start with some polls, some interesting polls for the audience. Yeah, so may I invite all the speakers to turn on the video, and let me run the first poll. Okay, I hope that you see a question popping up on your screen. We'd like to know whether you calculate the uncertainty of your qualitative analysis. We have 50% responses, so let's wait a little bit more. Okay, so 60% of our audience have responded and the numbers are not increasing very much. Let me end the poll and share the results. So it appears that majority of our audience do not calculate uncertainty of their qualitative analysis results, which is not surprising as compared to quantitative analysis. So Steve, Ricardo, and Gunnar, is this result surprising to you?
Good. I'm happy with numbers. 24% are trying to do it. I think the numbers are nice, I would say. Probably the people that are interested to the topic, or at least that one, that 25%, 60% that do this calculation, for sure they were interested with the topic. So I'm surprised with a large number of yeses. I don't know.
I would agree to that. I'm surprised that 24% of the participants do calculate uncertainties. I had expected that figure to be lower, actually.
Yes, I think I'd agree. Although, if we recall that we've been including things like false response rates as metrics, it would be much less surprising if folk were at least tracking false response rates, and you might have expected quite a lot of people to be doing that. So, but the fact that some, a measurable quantity are doing so is quite reassuring and quite interesting.
Yeah. But let's hope the guide will allow to improve these numbers in the future.
Yes, certainly hope so. If we run the webinar again next year, the numbers might go up. Okay, so there is a second question for everyone. Let me launch it. I hope you see the question. Do you find it relevant to know the uncertainty associated with your qualitative analysis? Now that you've attended almost 3 hours of this webinar. Oops. Okay, I'm not sure why, but the poll stopped by itself. Okay, so I'm not sure why, but anyway, we have very fast responses for this. And it seems like, yep, we have a good majority finding it relevant to know uncertainty related to the qualitative analysis. So we should expect more people to implement the guide. Yeah.
Yes, I'm very happy with these results. Also, I think that people find relevant to monitor the performance of their qualitative analysis. And fantastic. I think that let's do it.
Steve,
Yeah,
Gunnar, do you have any comments?
I think it's clear that people are interested to know something about it. So yes, that is, again, very interesting, even higher than I had expected.
Right. Okay, I hope the third question will not stop by itself. Okay. For analytical methods that involve a quantification stage after a qualitative analysis step, do you perform independent assessment of the performance of these two analytical processes? So I think the next question would be, should we perform independent assessment of the performance of these two analytical processes?
Yeah.
Okay, the poll stopped by itself again. This is strange. Okay.
Timed polls.
Okay. Yep. Almost 60% to 40% more yes than no. So I guess the audience would be interested to hear from the experts here. What would be your advice?
Steve, do you want to start now?
Well, I've got a reaction. I don't know whether it's a considered opinion. This is a little bit like a number of other validation problems where you can either treat your process as a black box, or you can open the box and look at the parts. And both of those are viable ways of proceeding if you're only interested in the outcome. So if what you're interested in is whether your screening and quantification process produces accurate results at the end, then there is no particular need to evaluate each process separately. If you're looking to improve the process, then it can be important to look at the two parts separately to find out which one is causing you, unduly high failure rates, for example. So I think the answer to this will very often depend on exactly what people are trying to achieve by evaluating the performance. The baseline is treat it as a single black box, a single process, and evaluate that. And that I would have thought would typically satisfy, say, 1785 requirements if the capability is purely for quantitation after checking for identity. But I think you would have to go further if you were using the two or reporting the two results separately, or if you wanted to improve the process and were not sure which part of the process was causing your problems.
Yes, yes, if I can, yes, I would say that yes, any option should be fine in this regarding this matter. I would say that the assessment of the performance of the quantification and qualitative analysis stage should be integrated somehow, at least to save experimental resources, save time in collecting the experimental resources, and then probably data processing will be a little bit independent. But okay, that yes, I find this balance interesting.
I would like to comment that this question points to the difference between the nominal property and the ordinal quantity, which I tried to illustrate in my presentation of the Vim approach to nominal properties approach. And if you consider to validate new methods and compare new methods with old methods, I think it's necessary to consider both parts, both the identification challenge and the quantitative challenge. So you have to have figures and metrics for both types of performance when you validate new methods, for example. But for the end user, it's the combined output, of course, that is of interest regarding the quality of the result.
Thank you. So we have 7 minutes more to the end of this session. I will run the last poll. There are some questions still coming in, but I will, what I will do is I will collate them and invite the speakers here to probably reply to you separately. I hope this is okay. So the last question for the day before we end today's session is for the identification of trace levels of analytes. Do you assess the qualitative analysis performance at different analyte concentrations? Okay, we have 50% of the responses. So yes, the majority says yes. Yeah. So any thoughts on this?
Can we ask Gunnar to start this time? Okay.
It's again the question of if we, by qualitative analysis, denotes the identification or its identification of a substance, or it's something else. If you think about qualitative analysis as an ordinal quantity here, you of course you have to check the performance at different analyte concentrations.
Steve, Ricardo, any thoughts?
I'm happy to see that people are checking the performance at different concentration levels. Yes, because typically in trace level analysis, your identification will be very, very demanding at low levels, and you have to monitor the performance at that low levels, and then expectedly it will improve as the analyte concentration increases. So you would like to follow how much better the identification performance gets at larger concentrations to manage better the performance. So I think that is a good practice to do that assessment. You just need to assess at one concentration level, the lower one, I would say, if the performance is so good that you don't feel the need to assess the performance at a little larger concentrations, I would say. Steve, do you want to add something?
No, I agree. I think it's good practice to check at several concentrations in case the performance degrades unexpectedly at the low end, of course. But if you've got a particular requirement for performance at a particular level, then obviously it's sufficient to study the critical level that you're interested in. So if there's a regulatory requirement that you must be able to detect with 90% confidence at 10 ppb, studying at 10 ppb is enough.
Okay, thank you. So I think we will have to end the last segment of today's webinar. It has been a very long 3-hour session for all of us. And on behalf of all the audience, I'm sure we are all very appreciative of the efforts that speakers have put in to give us this comprehensive talks today. So great. many thanks to all of you. And before I end the session, I should rightfully give acknowledgements to the organizers. So let me share the screen. Okay, so before I close today's session, again, I'd like to thank the speakers, Dr. Gunnar, Dr. Ricardo Betancourt da Silva, as well as Dr. Steve Ellison for taking time, as well as the organizers, EURACHEM CITAC, HSA Singapore, and the sponsor, EUPAC, for organizing this workshop. As I have mentioned in the chat, you will be receiving an automated email from us. Okay, so there will be several emails. Tomorrow you will be receiving one from Zoom that is to gather some feedbacks from our audience today. So for the benefit of our audience, we will also extend today's recordings to your registered email. So please check your email from us before the end of February. And you can view the recordings as many times as you wish. So if you have attended today's webinar for more than 50% of the entire duration, you will be receiving an email with a link to download the e-certificate of attendance. So on behalf of the scientific committee for this workshop, we hope that you have found today's presentation beneficial, and I wish everyone a pleasant day ahead. Thank you for joining us today. Okay, goodbye.